I wish to thank organizers for giving me a chance to present our recent work. My name is Hanwool Koo. I'm working with my supervisor, Professor Arman Shafialu in Korea Astronomy and Space Science Institute and University of Science and Technology in South Korea. From now on, I'll talk about our 3 recent papers with the title of Cosmology with Type 1a Supernovae, Searching for Systematics and Model-Independent Reconstructions. For more detail, please see 3 papers on the slide. First, I'll give a brief introduction about the studies. Type 1a supernovae, in short SN Ia, are used as standardizable candles for distance measurement and have become an important portion of modern cosmology. However, the standardization is purely empirical and requires SN1A light curve fitting model with a number of parameters and hyperparameters. The light curve hyperparameters are usually constrained based on assumption of cosmological model, but we can find a model-independent manner to constrain the hyperparameters. In addition, to search for systematics in the SN Ia data, model-independent reconstruction is required. After reconstruction, we can look for features in the data which can be a hint for systematics or new physics. We can also perform model selection and parameter estimation without comparing models. To do all of this, we apply the iterative smoothing method, which is the non-parametric method to reconstruct the distance modulus and expansion history of the universe. This method starts from initial guess of distance modulus, but generates model-independent reconstruction of distance modulus with lower chi-scale value after numerous iterations. We can find equations for each iteration on bottom of the slide, and more detail in the paper. First, we talk about what we presented in the previous Cosmology from Home conference. To construct the distance modulus from the data and use them for constraining the light curve hyperparameters, we use the joint light curve analysis, in short, JLA compilation, which have light curve parameters information based on sawtooth feeder, and apply the tree formula on the middle of the slice. Among the parameters of the formula, 2 proportional factors, alpha, beta, and the 2 absolute B-band peak magnitude parameters, large MB1 and delta M, are light curve hyperparameters that need to be constrained, while others are light curve hyperparameters provided by JLA. We assume 3 different cosmological models for the analysis. One is ΛCDM, lambda cold dark matter model, which have equation of state parameter with respect to redshift equals to -1. Another is CPL, Chevalier-Polaski-Linder parameterization, which parameterize the equation of state parameter at low redshift. The other is PEDE, phenomenologically emergent dark energy model, which claims no effective presence of dark energy in the past, then emerges at later times. We compare hyperparameter constraints of the 3 models with 3 different colors with those from the reconstructed distance moduli, colored in red. As we can see on the right corner plot, contours are all consistent with each other, which indicates that there is no dependence on cosmological model. One exception is that large MB1, one of absolute B-band peak magnitude parameters from reconstructions, shows uniform distribution because SN Ia alone cannot constrain an absolute distance scale. Next, we divide the data into 2 redshift bins with equal sizes and compare the constraints from the reconstructed distance moduli. We can see that statistical deviations between the 2 contours are not large enough, which indicates that there is no clear redshift evolution. Based on the equations on the slide, we have derived the expansion history of the universe and 2 parameters which describe dark energy properties of reconstructions with higher likelihood than that of the best fit ΛCDM model. We adopt the Ohm parameter, which introduced by Stani, Shafialu, Starobinsky in 2008, since it is equal to the matter density at present time when background model is the ΛCDM model. In other words, it can be useful to test the ΛCDM model. On this slide, Top left panel shows relative deviation of 8,000 reconstructed distance moduli from the best fit lambda CDM model with a constant shift, while others show reconstructions of the auto parameters derived from them. We have produced 20 reconstructions from each of the 4 different initial guesses and each of 100 random Likert hyperparameter values. We find that reconstructions are consistent with the prediction of lambda CDM, allowing some additional flexibility. From now on, we talk about looking for features in SN Ia data using the more recent Pantheon data. We find oscillating features in the Pantheon data at redshift lower than 0.5 around the best fit lambda CDM model. We have tried to see how generic such behavior is found at many Monte Carlo realizations of the data using the full covariance matrix of the Pantheon data. On this table, the 2 circles shows that the deviations of the redshift-binned best fit parameter values from their full dataset best fit values are larger than or comparable to 1 sigma, which indicate oscillating features. We find that such features occur in about 4 to 5% of Pantheon-like simulations. We think that it might be a hint to possible systematic or new physics. Finally, we talk about direct model testing. We do this because model testing using Bayesian analysis depends on comparing models. We try to test consistency of a model and the data without comparing different models. By estimating likely distribution of delta chi-square using iterative smoothing method for model selection and parameter estimation. For this analysis, we assume lambda CDM, Pede model, and the kink model, which introduced by Corasaniti and Copeland in 2003. Based on previous works, we select certain model parameter values that shown on bottom of the slide as an example. For model selection, we define delta chi-square as chi-square difference between smooth reconstructions and model best fit initial guess. Remember that the iterative smoothing method starts from initial guess. We can see that likely distributions of delta chi-square for 3 different model best fits using 1,000 Pantheon-like mock realizations based on 3 different fiducial models are the same with each other, which indicates there is no dependence on cosmological models that are used for simulations. And for parameter estimation, we use the fiducial models as initial guess for defining delta chi-square. In this figure on the slide, we can find that the Likert distributions are the same with each other, which indicates no dependence on cosmological model again. This figure shows estimated constraints on the matter density at present time for 3 different models using 95% confidence limit from Pantheon. We can see that they are highly distinguishable with one another. Next, we perform model selection with future data, which is 1,000 forecasted WFIRST mock realizations based on lambda CDM fiducial model. Note that the official name of WFIRST has changed to Nancy Grace Roman Space Telescope. As shown on the figure and table on the slide, the likely distributions for the 3 different models and their estimated type 2 successes, which indicate the number of cases that the wrong models are ruled out beyond 95% or 99% confidence limit, are highly distinguishable from one another. Now, here I summarize that we find no model dependence, no redshift evolution of Lie curve hyperparameters, and find that reconstructed expansion history and dark energy properties are consistent with prediction of lambda CDM, allowing some additional flexibility. We also find that about 4 to 5% of Pantheon-like simulations have similar oscillatory features with that in the Pantheon data, which might indicate systematics or new physics. Finally, we show that model selection and parameter estimation using the iterative smoothing method works well, which confront with Bayesian analysis. Our next paper in preparation is about confronting model selection based on conventional Bayesian analysis using Bayesian evidence. With that, based on frequentist analysis using the iterative smoothing method. Two plots on the slide from our next paper in preparation show that the true model is not ΛCDM or PETE, but Bayesian evidence distribution supports ΛCDM, while likely distributions exclude both models at a high rate. Please check the paper that will be uploaded on arXiv as soon as possible. Thank you for listening to our talk. Questions and comments are always welcome. And for more detail, please see the papers on the slide.